Let us go over the sample problem. Point loads of magnitude 100, 200, and 400 kilonewton act at B, C, and D respectively as shown in figure 3.3. Determine the increase in the vertical stress at a depth of 6 meters below the point A. Use Boussinesq's equation. So you have here the point load applied at the point B is 100 kilonewton. The point load applied at point C is 200 kilonewton. The point load applied at the point D is 400 kilonewton. And then we are required to get the vertical stress increase 6 meters below point A. So if we are to draw this figure in an isometric view, we have here your 100 kilonewton acting on point B. We have here your 200 kilonewton acting on point C, and then you have your 400 kilonewton acting on point D with the corresponding distances. So we are tasked to get the effect of these point loads at a point 6 meters below point A. So if this is point A, 6 meters below point A, what is the effect of the different point loads? So that is simply the summation of the vertical stress increase at point B plus the increase of point load at C, and then the vertical stress increase at point D. First method, let us solve the vertical stress increase by the equation. So we have here point B, the load that is being applied is 100 kilonewton, and then at point C is 200 kilonewton. And then at point D is 400 kilonewton. So from our sample point, 6 meters below A, what is the X distance? So this is our X distance, this is our Y distance, and this is our Z distance. From our sample point, the X distance with respect to point B is 6 meters. The Y distance is 0. So remember that the sample point is just below point A. So there is no Y distance. That's why it's 0. And then the depth is 6 meters. And then considering point C, the X distance is still 6 meters. The Y distance, so this is the Y distance, that is 6 meters. And then still the depth is 6 meters. And then finally at point D, from point D to our sample point, so if this is 3 meters and from point B to point A is 6 meters, therefore our X value is 3 meters. And then our Y value, our Y distance, that is 6 meters. And then still the depth is 6 meters. So since we already have the value for X, Y, and Z, we can now solve for the value of L. So this is simply the square root of 6 squared plus 0 squared plus 6 squared. So this is 8.4853. Next is the square root of 6 squared plus 6 squared plus 6 squared. So this is 10.3923. And then finally, square root of 3 squared plus 6 squared plus 6 squared. This is 9.0. So we know the value of P, we know the value of Z, we know the value of L. So we can directly substitute the equation. So for point B, this is 3 times the point load, which is 100, times the value of Z. Our Z is 6, divided by 2 pi. Our L is 8. So this is 0.2345. 5. Next is considering point C, simply substitute the equation, that is 3 times 200 times our Z is 6 cube divided by 2 pi multiplied by 10.3923 raised to 5. This is 0.1702. Then finally, at point D, this is simply 3 times 400 times the value of C, which is 6, divided by 2 pi times 9 raised to 5. So this is 0.6986. So therefore, total vertical stress increase at point A is the summation of the vertical stress increase caused by the 3-point loads, that is 0.2345 plus 0.1702 plus 0.6986. So this is 1.1032 kPa. So important reminder in solving the value for this part for the value of L, please do not round off. If you are to calculate the values for L, you save the values on your calculator. So do not use, say for example, this part 8.4853, but use the value that was calculated from the calculator so that we do not have a double round off. Okay, so same for here. If you are to sum all the vertical stresses due to point B, point C, and point D, save the values and then add them up so that it would not be a double rounding off. So next is by the use of table. So by the use of table, this is our equation that we are going to use. This is the same equation that we used a while back. However, it is simplified, and instead of substituting the other part of the equation, we simply have to get the value of I1 and then we substitute it to this equation. So since we are using the table, we need to get the ratio of R and Z. So again, our load at point B was 100. At point C is 200. At point D is 400. The value of R at point B, that is x squared plus y squared. So this is simply 6 squared plus 0 squared. This is 6. For point C, this is the square root of 6 squared plus 6 squared. So this is simply 8.485. And then at point D, this is 3 squared plus 6 squared, the square root of the quantity. So this is 6.708. And then we know that the depth of the sample is 6 meters. So from there, R divided by Z, 6 divided by 6 is 1. 8.485 divided by 6 is 1.41. 6.708 divided by 6 is 1.12. So since we already have the value of R divided by C, we can get the value of I1. So from the table, if the ratio of R and Z is 1, so the value of I1 is 0.0844. 0.0844. Next, if R over Z is 1.41, so this is 1.4 and 1.6, we do not have a value of 1.41 because 1.41 is somewhere here and we do not know the value. So this is the time that we are going to use interpolation. So if we are to interpolate this part, that simply becomes 0.02 minus 0.0317 is to 1.6 minus 1.4 is to 0.0317 minus, we do not know the value, divided by 1.4 minus 1.41. So x here is equal to 0.0311. So this is now the value of your I1. 0.0311. Next is 1.12. So from the table, we again see that there is no 1.12. So 1.12 is somewhere here between 1 and 1.2. So apply by interpolation to get the value of I1. And that is 0.0645. Let us now solve for the vertical stress increase. This is simply 100 divided by 6 squared times the value of I1, 0.0844. This is 0.2344. Next, this is 200 divided by 6 squared times 0.0311. This is 0.1728. And then finally, you have 400 divided by 6 squared times I, 0.0645. This is 0.7167. Again, please use the calculated values, store the values in your calculator, and then add them up to avoid double rounding off. So this is 0.2344 plus 0.1728 plus 0.7167. This is 1.1239 kPa. Answer.